Question 18 is about Graham's law of effusion. At 25 degrees Celsius, a gas effuses twice as fast as sulfur dioxide with this molar mass. The gas could be. Now you do need to know Graham's law, which basically says that the rate of gas A divided by the rate of gas B, and we're talking about the rate of effusion, is equal to the square root of the upside down, as I say, which is the molar mass of gas B divided by the molar mass of gas A. It's important to know that it's A over B on one side and then B over A on the other side, and it's the square root of the molar mass ratio. So let's plug in the pieces that we have. It says a gas effuses twice as fast as SO2. That means that SO2 is the slower gas because whatever this other gas is faster, right? So the other gas is slower. Now, also keep in mind that the slower gas is equal to the heavier gas, the one with the higher molar mass. So whatever gas is going faster than SO2, it's got to be lighter to be faster. So SO2 is the slower gas because the other one moves faster, and therefore it's the heavier gas. Now you can assign them things. That means we can call gas A, we can call this gas A, and this would be gas B. So look, we can go in here and replace some things. Gas A is the unknown, and gas B is SO2, which is a sulfur dioxide. That means we can go in here and replace gas B with SO2, and gas A is the unknown. What's the point of doing that? Well, since we know that gas A, the unknown one, is twice as fast, we can actually replace this entire ratio, because think about the fact that the rate of the unknown gas is 2 relative to the rate of SO2, which is 1. That's what it means when it says twice as fast. It's a 2-to-1 ratio. So this entire left side can just become a big 2. Now, we actually know something about the right side underneath the square root, and that is the molar mass of SO2, which is about 64.1. So let's replace that with 64.1 grams per mole, and then you just do some math. So you square both sides. Squaring both sides turns this 2 into a 4, and it gets rid of the square root symbol. And then you multiply both sides by the molar. Actually, you just switch them around, do your math, and you get this. Did not mean to do that. And here you go. The molar mass of the unknown gas is equal to 64.1 divided by 4. You get 16 and some change. So it's about 16 grams per mole. Then you're going to look over to your answer choices, and you're going to pick the gas that has a molar mass of about 16. Helium has a molar mass of about 4. Oxygen diatomic has a molar mass of 16 plus 16, which is like 32, so that's not good. H is 1, I is, just not okay. But methane does have a molar mass of about 16, therefore it's your answer. 19. A sample of hydrogen and a sample of nitrogen at 0 degrees and 1.2 atmospheres contain the same number of molecules. Therefore, they're also the same number of moles, by the way. So same N, which is number of moles. So you can also write it out as like the number of moles of H2 is equal to the number of moles of N2 in these samples. So what does that mean? Well, they have the same number of moles, so kind of like going through piece by piece. Same number of moles, same temperature, same volume. List out your ideal gas law variables, P, V, N, R, T, and check off things that make sense. Same temperature, R is the same number of moles, same pressure. That means they have to have the same volume. So let's go through the questions or the answer options and see what makes sense. Both have the same volume. That makes sense. So this one says different volume, so that means that this option cannot work because of this red part here. Neither the same volume nor the same mass. That's a lie. They do have the same volume per the fact that they have the same temperature, pressure, and number of moles, which is going to be number of molecules. Do they have the same mass? No, but a different average kinetic energy, different volume. So the part that makes this false so far is different volume. Same average kinetic energy, different volume, also out. Same volume, so far so good. But a different average, blah, 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 blah. Same volume, so far so good. Now we gotta talk about the same average kinetic energy. Here's the part that really that matters for average kinetic energy. Temperature. Temperature is directly proportional to the average kinetic energy. So because they are at the same temperature, they have to have the same average kinetic energy. So that part is true for the crossed out answer, but the whole answer is false because they do have the same volume. Same kinetic energy, average kinetic energy. Oh, be very careful. It must say average kinetic energy. So same average kinetic energy. So far, this last option is looking good. Different average kinetic energy, that's a no. Different, that's a no. This is just like a problem solving strategy to go through everything and see what makes sense. Okay, so we've gotten the volume part straight. They must have the same volume. They must have the same average kinetic energy. But obviously the mass of H2 and N2 are going to be different because they are different molecules, so they have different molar masses. So looking at that last thing, they are not going to have the same mass. Mass is not proportional. Remember, moles are proportional. Same mass, that's a no. Not the same mass. Not the same mass. Different mass, that's looking good so far, but that answer is overall false, right? Different mass, that's good, and this mass, that's good. So the answer is going to be the last one. They have the same volume, the same average kinetic energy, but a different mass. Now, if you look at the kinetic energy equation, let's say you have the kinetic energy of H2, and you have the kinetic energy of N2. Kinetic energy in general, and this is assuming one single point particle, is 1/2 mv squared. So I'm going to say 1/2 molecule of a mass of an H2 times the velocity of an H2 squared. And this is going to be equal to 1/2 of the mass of an N2 times the velocity of an N2 squared. At the same temperature, the average kinetic energy will be the same. So what that means is that this, move it this way, this equals this. Because if they're at the same temperature, then their average kinetic energies are going to be the same. What that means is we can get rid of all this, set them equal to each other, and you can do the math to sort them all out, but effectively what you get is the Graham's law equation. Now V, we replace that with R for rate because it's a little bit different. And then you get Graham's law. So it kind of shows you a bit about how Graham's law is related, right? Graham's law through a very simplified but some kind of process where you sort the M's and the R's just like you saw, there before I erased it. Number 20. What are the spectator ions and the reaction between solutions of ammonium carbonate and aluminum bromide? So to do this, you need to write out your reactants. So ammonium is NH4 with a plus, carbonate is CO3 with a 2 minus. So those are the ions. To make the compound, or either the compound or the formula for the solution, so to speak, you're going to need two ammonium, so it's going to look like this. And that is ammonium carbonate. It's going to, a solution of ammonium carbonate, so I guess I can put AQ just to be more precise. AQ, ammonium carbonate mixing with aluminum bromide. That's going to be here. So aluminum is 3 plus, and then bromide is -1, which means that if I actually want to get my solution, it's going to be 3 bromides. There we go. This is aluminum bromide, aqueous. Now, think about what are the possible products. So we know that the cations and the anions are going to switch places. So it's helpful to remember that the NH4 is a plus and You also have over here floating around in the solution, you have the carbonate, which is a 2 minus. And then over here in the solution, also the other solution I should say, you have aluminum, which is 3 plus, and you have bromide, which are minus. So this is like the molecular form of the equation. You can also transform this into the net, or into the ionic and then the net ionic. So here's what that would look like. Because these are both solutions, I could also have written them out like this. In the red solution, so to speak, I have 2 NH4 pluses and a carbonate. Plus, and then I have Al3 plus 3 bromides. Now, what are the possible other sides? Remember that you're going to have your cations pair up with the opposite anions like this. So the one of the products, so to speak, is going to be ammonium bromide. It's going to look like this. It's going to be NH4Br. Now the reason that you just need one of each is because there's a single plus and minus on the bromides. We'll deal with the balancing part later. And then you also are going to get Al, which is a 3 plus carbonate, so it's going to be Al little 2, and then the carbonate is going to be CO3, but you need multiples of them. You actually need 3 of them. All right. Now, in terms of balancing, you always want to make sure you have your charges balanced. I'm going to duplicate these. That way you can see what's going on with them. Remember that for these types of equations, one of them is going to be one of them might be the precipitate, and one of them might not be the precipitate. You got to look at your solubility rules. So we have carbonates, and we have a carbonate and a bromide. Let's see. There we go. So carbonates are not soluble unless it's paired with something from group 1 or ammonium. So let's take a look at our carbonate. Carbonate here, this carbonate is going to be paired with neither a group 1 nor ammonium. So this is going to be our solid precipitate. But we need to verify that the NH4Br is going to be aqueous. It's going to remain aqueous. So looking back at our solubility rules, bromides are aqueous. Bromides are going to be soluble unless they're with some exception, but ammonium is not one of those exceptions. So this is going to remain aqueous. And I'll put the AQ here as well. Now, what does that mean for our molecular formula? Well, for the top one, we don't have to really change anything. We have everything. We have the ammonium carbonate mixing with aluminum bromide to produce ammonium bromide and aluminum carbonate. This is our precipitate, which means it's going to stay together in this form. But if you want the ionic thing, splitting it all apart to get our total ionic equation, we need to split this up because it is aqueous, right? Our solubility rules say that ammonium and bromide are going to be split. Let's balance it out first. We don't want anything weird happening. So going back to the top, 2 ammoniums, put a 2 there, 2 bromides. So that needs to actually be a 6, a 2, 2, carbonate, 3 carbonates. Okay, good. All right, so this is balanced. We have 6 ammoniums on the left and the right. We have 3 carbonates on the left, 3 carbonates on the right, 2 aluminums on the left, 2 aluminums on the right, and then 6 bromides on the left and the right. Carry those changes through. Put a 2 here. A 6 there. We're going to have 3 of these. 2 aluminums. Okay, that part's good. And then on the other side, I'm going to move these because this room's getting kind of tight. We know that the aluminum, that's going to stay over there. We need to split this apart. And also keep with our balancing. We're going to have 6 here, and that's going to say how it is. So what it's going to actually look like is going to be 6 ammonium ions, and we have our 6 bromide ions, and of course we still have, move this way, we still have our precipitate. Actually, I still don't have room, so I'll move that there. And we still have our precipitate, which is hanging out as well. All right, so our net ionic, which gets rid of all of our spectators. Actually, we'll cross out spectators in purple, I guess. So looking on the left and the right, we have 6 ammoniums. We have 3 carbonates on 3 carbonates, but carbonate and aluminum are actually going to be the key things that create that precipitate. But here, and this should say 6. Forgot to update it. And then here we have our bromides. 6 on the left, 6 on the right. So our net ionic equation is going to look like this. Duplicate. So we have carbonate and aluminum. Does not matter the order really. So we have these 2 things. Duplicate. Creating our precipitate. So what is missing? Or in other words, what did I cross out? Ammonium is going to be a spectator along with the bromide because they did not participate in the formation of the precipitate. That was a long roundabout way because there's so many ways to do it. But effectively, you need to write out your equation, balance it, and then split it apart. But look at your solubility rules, and remember, don't split apart the product that is not actually soluble. This is insoluble, so it's going to be a solid. It's your precipitate. The other stuff, the ammonium bromide, so to speak, that would be split apart to make, it's just going to be floating around in the solution. And of course, these are aqueous, and those are also aqueous, but I just didn't put that. So what's the answer? The answer is going to be the ammonium and the bromide ions because they are not participating in the formation of the precipitate. Tony 1. What mass of precipitate is produced when 42 milliliters of a 1.42 molar calcium chloride solution reacts with excess solid sodium phosphate? Excuse me. So you have a volume and a molarity. This is really like stoichiometry mixed with molarity. So step 1, recognize you have a volume and a molarity of calcium chloride. So molarity is equal to moles over liters. Rearrange this to get moles. So you get that moles is equal to molarity times the liters. And that's going to be equal to the molarity of 1.42. Don't forget your volume needs to be in liters. That's going to be 0.042. Don't forget, divide that by 1,000. And how many moles is that? 1.42 times 0.042. You get about 0.05964. We're not caring about sig figs right now. And that's going to be moles of calcium chloride, which is CaCl2. All right, now that you have your moles of calcium chloride, which is important, then you got to do stoichiometry with it. So step 2, we're going to take our 0.05964 moles of CaCl2, and luckily we are given a balanced equation, so that's good. And we're going to turn our moles of CaCl2 into moles of what we care about. Now we're looking at this and we're like, which one's the precipitate? From experience, you might recognize this. NaCl is very soluble. It just makes salt water. But phosphates are not soluble, typically. So let's look at our solubility rules again. Calcium phosphate is a phosphate. Phosphates are insoluble unless it's with something from group 1 or ammonium. Calcium does not fit that. Therefore, this is our precipitate. So since that's your precipitate, that's what you're actually working toward. This question is a little tricky because you have to figure out what your precipitate even is. So if you do your stoichiometry and you inadvertently put NaCl, you'll be wrong because that's not a precipitate. You need to put the right precipitate, which is calcium phosphate. And looking at your molar ratios, 1, oops, that's a 3. 3 is going to go in front of the calcium, and then in front of the calcium chloride, and in front of the calcium phosphate precipitate, it's a big invisible 1. And then of course, one more step, I'm going to shrink all this down so we have some space. And then lastly, you need to convert your moles of calcium, let's see, Ca3PO4. Convert your moles of calcium phosphate into grams of calcium phosphate. And that requires you, you have to find the molar mass of it. So let's find what that is. And magically, we find that the molar mass of calcium phosphate is about 310.2 grams per mole. And if you do all the math here, you're going to find out what the mass of that precipitate is. So this times 310.2, divide that by 3, and you get about 6.166 and some junk, so it's about 6.17, and that's your answer. And then last one for this video is going to be, under the same conditions of temperature and pressure, how does the density of carbon monoxide compare to that of hydrogen? So you can use the full density of a gas equation. So up here we derived it to be this thing here. So let's copy and paste. So you can use this if you'd like, but we don't know the conditions. It might be STP. Let's actually just assume it's STP. So with that being said, we can actually simplify this equation because the density of a gas at STP, is simply equal to the molar mass of the gas, which is going to be measured in grams per mole, and you divide that by 22.4, which is the unit, which is the volume of a gas at STP, which is liters per mole. Now this is one way to do it. I just find this to be a quick, fast way to do it, something like this. So look at how the units cancel out. Moles are going to cancel, and what you actually get is the relative density of these two gases at STP, which are going to leave over the units of grams per liter. So let's figure out the density of the carbon monoxide and that of hydrogen. These are relative densities. We don't know the actual conditions. We can't give you the actual densities. But under the same conditions, they will have the same relative. Their relative densities will be locked in. So density of carbon monoxide is going to be the molar mass of carbon monoxide. It's like 16 plus 12 is 28. 28 grams per mole. And we're assuming these are STP conditions. We don't know the conditions, but it's easy for us just to make that assumption. Move that out of the way. 28 grams per mole, we're going to divide that by 22.4 liters per mole. And we get that the STP density of carbon monoxide is some number. It's 28 divided by 22.4. Roughly 1.25 at STP. And you could always verify on your own that under standard conditions, this is what it becomes. You can do the derivation. And then let's do the carbon monoxide or the hydrogen gas density. The density of hydrogen gas under STP conditions is going to be just around 2. So that's the molar mass of hydrogen, 2 grams per mole. And we're dividing that by still 22.4 liters per mole. And we get 2 divided by 22.4. About 0.09, very roughly. Now it's asking, how does the density of carbon monoxide compare? So you need to compare this number to this number. You can easily divide, right? This divided by that. And you get that this number is 14 times greater. And there you go, that's your answer. I just divided 1.25 by 0.09, and it turns out that carbon monoxide is about 14 times more dense than hydrogen gas under the same condition. So whether it's STP or not STP, remember, this is just showing you the relative density, this calculation set here. If you really were feeling it, you could totally fill out conditions that you want to, but you're going to be maybe frustrated that you don't know the temperature and you don't know the pressure, even though you know molar mass and R. So just assume that the temperature and the pressure are just standard. And to do that, you can actually just divide the molar mass by 22.4.